All right, in this video, we're going to cover function composition. And basically what that means is that we are going to essentially stuff one function inside of another function. So if we have f of g of x, what it means is first we're going to take x and we're going to feed it into g. It's going to produce an output. That output then gets put into f, and then that produces an output. So it kind of goes like this. So here's the f of g machine. Right, so we have x, it gets fed into g, and it spits out something else. That something else gets fed into f, and then that produces f of g of x. So you always want to start with the function that's closest to x. Like, so for example, you want to have g be applied to x first, then you're going to apply f. All right, so this is all just saying the same thing. The last part here is just warning you that in general, f of g of x is not the same thing as f of x times g of x. Also, in general, it's not always the case. I don't think they said this. You might want to watch out for f of g of x is in general not equal to g of f of x. So order definitely matters. Oh, there it is. Right, so this is commutativity. So example 2, determining whether composition of functions is commutative. So commutative just means that. It means, is it true that f of g of x equals g of f of x? So I think this is a great place. So let's just compose some functions. So f of, actually, let's start with maybe a concrete number. So like as a warm up, let's just begin here. Let's say we do x equals 1. So if I wanted to do f of g of 1, and I also wanted to do g of f of 1, this is how I would do it. So f of g of 1, what I'm saying is that this is f of g of 1. Okay. G of 1, so we're given here that g is equal to 3 minus x. So this is equal to 3 minus 1, right? So that's going to give me 2. So that's what now I'm going to plug into f. So this equals f of 2, because g of 1 was 2. So now what I'm going to do is I'm just going to evaluate f of 2. So f of 2, now look at what f is. It's saying 2 times the 2 that came from g of 1 plus 1. And so this equals 5. If we look at that in our fog machine, if you will, so remember that we took 1 and we put it into g. If I feed a 1 into the g machine, it spits out a 2. Then what I do is I take that 2 and I put it into the f machine. So f of x says double it and add 1. So if I put a 2 into the f machine, it's going to produce 5, which is exactly what we got. Right, so that's function composition. So let's let's try it again with g of f of x, just for practice. So that was f of g of 1. So let's try g of f of 1. So by this, I mean g applied to whatever the outcome of f is when we feed it 1. So kind of just want to look at what f of 1 is. F of 1 is 2 times 1 plus 1. So that's going to give me 3. So this is my input now for g. So this is going to give me g of 3. G of 3, what does g do? G does 3 minus x. So that's 3 minus the 3 that I got from f. And so this is going to be 0. So we can already see that they're not equal, because if you say two functions are equal, what you're really saying is that at every single point in the domain, they take on the same value. And they don't match when x is 1. So sorry, you're not equal. But we'll show it like with a general x as well, just for fun. So let's take a look at kind of the machine here. So this was f of g. Let's look at the g of f machine. So the g of f machine means that we're going to take 1 and we're going to plug it into f first. So remember that f of x is doubling plus 1. And when I put a 1 into that machine, it spits out a 3. I take that 3 and then I shove it into g. G of x is equal to 3 minus x. And when I put a 3 into the g machine, it produces a 0. And that's my answer. So I'm more than happy with anyone who prefers to evaluate composed functions at a point using this diagram. I think it's great. Let's see. All right, so now we want to actually kind of just look at it in general. So let's try to remember 2x plus 1 and 3 minus x as I scroll away from our problem. So maybe we'll switch colors here. So I think what I want to do is just split the page down the middle. So on the left-hand side, we're going to do f of g of x. And on the right-hand side, we're going to do g of f of x. So this will be g of f of x. And then this will be f of g of x. All right, so, okay. I actually, sneaky. I'm going to steal my functions from right there. Perfect. So f of g of x, f of g of x. So instead of writing g of x, I'm just going to replace it. I'm going to write what g of x is, which is 3 minus x. Right? So all I did was just replace that g of x with its explicit form, 3 minus x. Similarly, if I was doing g of f of x, what I would do here is I would replace f of x with whatever its explicit formula is. So that's going to be g of f of x was 2x plus 1. Right, so I'm just rewriting it with what f of x and with what g of x really are. So the next thing I want to do, I'm going to go back to my fog example. What this is saying is that into f, I want to plug in 3 minus x. So f is the function that says 2 times your input plus 1, right? That's what f does. I give it a number and f's like, okay, I'm going to double you and I'm going to add 1. If I gave it a cheeseburger, it would double the cheeseburger and add 1. If I gave it like a unicorn hoof, it would double it and add 1. So I don't care what I'm putting into it. I just need to know that I'm doubling it and I'm adding 1. So In this case, what I'm putting into it is 3 minus x. On the other hand, with g, what g does to a function is it just says, okay, whatever you're giving me, I'm going to subtract it from 3. So it's 3 minus cheeseburger, unicorn hoof, whatever. Whatever I tell it, it's like, okay, I'm just going to subtract that from 3, and then that's my output. So meaning I'm just going to shove 2x plus 1 in there. So this orange 3 minus x, that's called the argument of f. It's just the thing that you give to f, and then f does some magic on it. Similarly, 2x plus 1, that's the argument we're plugging into g, and then g just is like, okay, give me your argument. All right. So that's the official term for it, the argument. And now all we have to do is we just have to simplify. So the hard part's done. Big brain moment is over. So now I'm just going to, nope. I'm just going to distribute my 2 over the 3 and the x. So this gives me 6 minus 2x plus 1. So this is 7 minus 2x. And then over here, I'm going to get 3 minus 2x, right? Because I have to distribute the negative over both, minus 1. And so this is going to give me 2 minus 2x. So I hope we can all agree that 7 minus 2x and 2 minus 2x are not equal. All right, so the next thing we want to do is we just saw how to evaluate a composite function algebraically, right? That's what we did in the first part here. That was the algebraic version. The next thing we want to do is we're going to use a table. So I think this is pretty fun. I hope you enjoyed as well. So we're going to just do it for a point, right? So we've got f of g of 3, and we've got g of f of 3. So remember, you always want to work on from the inside out. So I'm going to start here with g of 3. So g of 3 is 2, okay? G of 3 is 2, so I'm just going to make a little note right here. G of 3 equals 2. So that means that I'm going to have f of 2, where that 2 is the artist formerly known as G of 3. And I'm going to do a similar thing over here with f of 3. So f of 3, I still need to be looking at 3, but I'm looking at f, right? So what I have here is that f of 3 is equal to 3. So if I'm writing this, my next step is that I still have g. I haven't done anything to the outside yet, but on the inside, I know that f of 3 was equal to 3. And I want to be super duper clear on this. The 3 that I put into f is not the same 3 that I'm putting into g. I didn't just like conveniently forget that f was there. It's just because f of 3 is itself 3 again. So, all right, so now I'm ready to evaluate g of 3 and f of 2. Well, I already know that g of 3 is equal to 2 because I already figured that out earlier. So this guy's done. But I need to also know f of 2. So f of 2 is 8. So that's how you would do it from a table. All right, let's do it for a graph. So fun. So I have G listed here on the left and F on the right. They're both parabolas. and I want to compute g of f of 1. So, sorry, no, I don't. I want to compute f of g of 1. So remember, that's f of g of x. We might see it like that. And that means the same thing as f of g of x. So what we have is that f of g of 1, f of g of 1. So the first thing I want to do is I want to plug in 1 into g. So maybe I'll do this simultaneously through my fog machine. So g of 1, where are you at? G of 1 is I go over to 1 and I look up to see how high it is. It's 3. So this thing's going to spit out a 3. Cool. And then I need to shove that 3 into F. So maybe I think about it in terms of my F machine. Right, so this was G. And when I plug in 3 into F, what happens is, what does happen? What comes out the other side? So F of 3, that means I come over to 3 here, and then I go up to see how high it is, and I get 6. So 6 is F of 3. So that's 6, 6. So those are the two ways you can kind of go at it. Maybe let's try another one. Maybe let's try to do, just for grins, G of F of, I have to choose wisely. So let's do G of F of, pick a good number. That's not going to give me, oh, you know what? Whatever, it doesn't matter. Let's do, perfect. Let's do 5. G of F of 5. Okay, so I'm going to have down here, so this was my fog machine. I'm going to zoom out a little bit, make some space. And then this will be our G of F of 5. So I'm going to take 5 and I'm going to stick it in the F machine first. And you might be being like, well, the G came first. And I was like, yeah, it is. But, you know, the cool thing about math is it's not always left to right. Okay, so first I'm going to plug it into my F machine and see what comes out, because that's what the notation says. So F of 5, let's see if we can figure this out. So I come over to F, I'm going to go over to 5. Okay, cool. Then I'm going to go up. Okay, nice. So F of 5 is 2. So this guy spits out a 2. And then what I want to do is I want to shove that into G. So I'll put this in my G machine. And this is going to give me, what does this give me? G of 2, what are you? So now I go over to G and I have to go all the way over to 2 and see what it is. And I'm like, oh, it's 0. Cool. So I just get 0. Right? So you're just kind of chasing it around. All right, so the next way we're going to do it is we're going to evaluate a composite function algebraically. So in this case, we want to do this is f of h of 1, which is the same thing as f of h of 1. I personally like the parentheses better because to me visually, I'm so used to PEMDAS thinking like, okay, you have to work inside the parentheses first. So to me, this tells me, okay, you need to work on h of 1 first before you can start working on f. When I have the open dot circle notation, I mean, I know what it means, but I'm just saying like, I just think it's less clear to the reader. Anyway, so I need to figure out what h of 1 is. So I do like this machine thing. So 1 goes into the h machine, where h of x equals 3x plus 2. So if I put a 1 in there, right, so 3 times 1 plus 2, that gives me 5. So I'm going to get a 5. So 5 gets spit out. And then that 5 gets shoved into the f machine. So this is exactly what we did on our first example. So f of x, what is f of, okay, what, so annoying. Cool. They switched up between x and t. Not amused. Anyway, x squared minus x. So in this case, I'm going to take that 5. So I got to do 5 squared minus 5. So that's 25 minus 5. So that gives me 20. And so now my output is 20. Right? So that's kind of how I look at it. I'm going to show you another way to maybe work it out. You might see some notation that goes like this. You might see something like f of h of 1 equals f of, and they'll just work it out straight in there. They'll be like, oh, that's 3 times 1 plus 2. And then they'll be like, okay, now I'm still working in my parentheses. That's f of 5. Okay, then that's t squared. 5 squared minus 5. So that's going to be 25 minus 5, and that's 20. So in this setup, it's the exact same thing, but you're just kind of showing your work within the line itself versus here we did it using the machine and we kind of did a little scratch work on the side. Either is fine, whatever you're comfortable with. So the next thing we need to do now that we are masters of composing functions is we need to determine the domain of composite functions. So, okay, because let's think about this in terms of a machine. X goes in to G, right? So, I mean, certainly, let's just think about the domain. So let's just think about the domain. Let's say it's all real numbers, like best case scenario, like great. Okay, fine. But X has to go into G. So we have to trim the fat a little bit. So like, okay, well, it's all real numbers that can go into G. So now it's the domain of G, right? Well, I have another issue. This is going to come out and it's going to go into F. So now the range of G becomes the input for F. So if G produces a number that F, I'm going to say doesn't like, meaning it's not in the domain of F, then we have to prevent that as well. And I just realized that explanation was not great. So let's just do some examples. Alrighty. I need more space. F of G of X. So this is going to be F of G of X, which is 4 minus 3x minus 2. So first I'm going to start with, and I'm going to do this two ways. So if this way you don't like, just wait 5 minutes. The domain of here, of G, right? We have to make sure that 3x minus 2 doesn't equal 0. So that's the same as x not equaling 2 over 3. So right off the bat to start with, I'm just going to make it our no-no list for our domain. Our no-no list is 2/3, okay? 2/3 has already been fired. We haven't even done anything yet. That's because G is going first. So, okay, we're saying that we're not going to allow 2/3, so we're good. But now what happens is F is 5 over x minus 1. So I need to make sure, because now this is where it gets weird. So F is 5 over the argument minus 1. Remember, our argument is G. I'm putting G into F. So this is 4 over 3x minus 2. So I'm also in the predicament where I need to make sure that 4 over 3x minus 2 minus 1 also doesn't equal 0, because, right, that's F is having its variable in its denominator. So I need to make sure that this doesn't happen. So this is the same thing as saying, okay, well, I just really need 4 over 3x minus 2 to not equal 1, right? Which we kind of saw that coming, hopefully. All right, let's solve this non-equality. So I'm going to multiply each side by 3x minus 2. And in general, you want to make sure when you're multiplying each side, especially by a variable, you have to make sure that you're not multiplying by 0. So for example, if I had 5 over x, and I wanted to make sure that it's not equal to, say, 1, well, if I multiply something by 0, I'm going to end up with 0 not equal to 0 on both sides. And that's not true. Of course, 0 is 0. Another weird explanation. I'm on fire today, whatever. So we know it's not 0 because we've already precluded the possibility of 2/3 being x. Okay, so now I get 4 is not equal to 3x minus 2. I'm going to add 2 to both sides, so then I get 6 is not equal to 3x. Okay, I'm going to divide by 3. 2 is not equal to x. So the other member of our no-no list is 2. So, boom. So what is our domain? We can't have 2/3 and we can't have 2. So the domain of f of g of x equals negative infinity to 2/3 union 2/3 to 2. And then 2 to infinity, right? This is the very elegant way of skipping 2/3 and 2. And you might be thinking like, well, couldn't we just have like simplified this all out? What would happen? Couldn't we like, did we have to check G first and then check F? Like, what if we just smooshed it all together and then just, see where the chips lie? So let's see what happens when we do that. So what I'm really saying is, can we inspect the domain after simplification? So let's look at what that would be like. So f of g of x, and I'm just throwing caution to the wind. And I'm just going to go for it. I'm going to say that this is f of 4 over 3x minus 2, right? We already did this, but so then this is 5 over 4 over 3x minus 2 minus 1. And you might be thinking, okay, well, how am I going to simplify that? It's not that bad. You just need to convert the 1 to a common denominator. So let's just kind of take a quick aside here. So I'm looking at 4 over 3x minus 2 minus 1. So, all right, what if I told you that you could do this? 3x minus 2. 3x minus 2 over 3x minus 2, right? Anything over itself is 1. So I just very sneakily made that a 1. And now that I have a common denominator, I'm all set. So I've got 4 minus 3x minus 2 over 3x minus 2. And so this is going to give me, these things are all equal. So this is going to give me 6 minus 3x over 3x minus 2. Okay, cool. So now I'm going to shove that back here. So this equals then 5 over 6 minus 3x over 3x minus 2. So keep, change, flip, whatever you want to call it. This is going to be 5 times 3x minus 2 over 6 minus 3x. One more step to simplify, I get 15x minus 10 over 6 minus 3x. And so if I gave you that function, you'd be like, oh, well, I just need to make sure that 6 minus 3x, like when does that equal 0? Okay, so I'm going to have 3x equals 6, so I'm going to get x equals 2. And you would say, okay, well, my domain for this function is negative infinity to 2, and then 2 to infinity. And so you actually lost, a member of the no-no list, because we didn't properly identify 2/3. So that's why you have to check first your domain of G, and then you have to make sure that your output of G is in the domain of F as well. I hope I convinced you. All right, so the same thing is going to happen in example 9, which happily is our last example. So the first thing we want to do, so since we're doing f of g of x, right? So that's going to be f of g of x, which is 3 minus root x. So the first thing that we notice is the domain of G. So let's make our no-no list. I know from here that x has to be greater than or equal to 3, right? Because here, maybe I'll put it in more clear terms. We know that for radicals, you have to be at least 0. So what I'm going to get is that 3 is greater than or equal to x. So as long as x is bounded above by 3, I'm good to go. But if x is bigger than 3, then I'm in trouble. So the no-no list is any x that's strictly larger than 3. Can't have it, right? Because the domain of G is all x that are less than or equal to 3. So now that we have that settled, and now that I realize I had a glaring typo, so this is the square root of 3 minus x. And then what f does to a function is it adds 2 to the argument and then square roots it. So it's going to take this guy and then it's going to add 2 and then it square roots the whole shebang. So this is kind of a trip because there's not much I can do to simplify this, first of all. And I never want to see a square root inside of another square root ever again, but I guess this is just the cards we were dealt today. If I wanted to know the domain of this, I need to make sure that the square root of 3 minus x plus 2 is greater than or equal to 0. Wow. So I'm going to subtract 2 from both sides. So I get 3 minus x is great. The root of that is greater than or equal to 0. Then I'm going to square both sides. So I get 3 minus x is greater than or equal to 0 squared, which newsflash, that's 0. I'll rewrite that. Oh, wow. I am really on a roll today. -2. -2 squared. 4. All right. We're in better shape now. I'm going to add x to both sides. So I get 3 greater than or equal to 4 plus x, and then I'm going to subtract 4 from both sides. So I get -1 is greater than or equal to x. So as far as our no-no list is concerned, we also have x bigger than -1. Right? So let's look at this from a number line perspective, because when we have compound inequalities, it just kind of melts the brain a little bit. So we need, let's look at this in the affirmative case. So things that are in the domain of G. Let's see. So -1, let's see, 0, 1, 2, 3, 4. Okay. In the domain of G, x has to be less than or equal to 3. So that's here, less than or equal to, Yep, okay. In the domain of f of G, we also found that x had to be smaller than -1. Well, I need both of these things to be true. I need to make sure that my domain is both green and purple. So the only time that happens is when I'm less than or equal to 1. It says both have to be satisfied, and I'm talking about both conditions. I have to be less than or equal to 3, and I have to be less than or equal to 1. So both have to be satisfied, meaning our domain for fog is negative infinity, comma, -1, closed bracket. And I think that does it. Good luck, and we'll see you soon.